Today we look at general plane motion of rigid bodies. Our equations of motion will be similar to those we looked at earlier for problems involving rotation about a fixed axis. We can sum forces in the x and y directions, set them equal to the mass times acceleration, recalling that because of the fact that the acceleration of different points on the body are going to be different, we have to be specific that it's the acceleration of the center of mass in both the x and y directions. We may prefer to use normal and tangential directions instead, depending on the geometry of the problem. And for our moment equation, we can either sum moments about the center of mass, like an axis through the center of mass, equal to the mass moment inertia about that same axis times the angular acceleration alpha. Or we can take the sum of the moments about any point. We just have to include the kinetic moments. And again, drawing a kinetic diagram will help to identify those and as to how far away they are from the point in the direction of the motion, a direction of the moment. And we can also sum moments about a fixed point. Well, there's not really a fixed point in a general plane motion body, but there is the instant center, which has again a velocity of 0 at that point in time. So it's like the body is rotating about that point at that particular instant, and we can sum moments about that point as well. So here's kind of a classic problem. We've got a cylinder, it's rolling down an inclined plane, and we want to know what its angular acceleration is, assuming that it's rolling without slipping. So drawing our free body diagram, we have the weight acting straight down, we've got the normal force, normal to the plane, and now if that's all we have, in other words there's no friction, then this won't roll, it'll just slide down the plane. For it to be able to roll, there's got to be this friction force. We can sum forces in the x direction, which will involve the friction force and the acceleration in the x direction. And to be perfectly correct here, I should have put the acceleration of the center point in the x direction. In the y direction, there's no motion, and so we can set the sum of the forces equal to 0. And now for our moment, we've got a choice. We can take the sum of the moments about that instant center, which I've identified as point O there, and set those equal to mass moment inertia about an axis through point O times alpha. Or, if we prefer, we can take the sum of the moments about the center of the wheel, which is its center of mass, and in that case, the only force that's creating a moment is the friction force. So, whichever way we do it, between the sum of the forces x and the sum of the moments about the center of mass, you can see there's three unknowns. There's the friction force, there's the acceleration of the center of mass in the x direction, and there's the angular acceleration alpha. But if we roll without slipping, then we know that the acceleration of that center point down the incline is going to be the radius times the angular acceleration. So now we have enough information to solve for our angular acceleration. Now here's a problem we've looked at probably a couple of times before, both with equations of motion and with energy methods, where we've tried to find the man's speed just before he hits the ground. Now when we did this before, we assumed that the pulley, that we could ignore the mass of the pulley. And we'll see how that's different if we say now that we're going to take into account the mass of the pulley. Well, we take the free body diagram of the man, and we can see that we've got a tension force acting up, the weight acting down, and we set that equal to the mass times acceleration, knowing that in this case the acceleration of the man is downward, so the negative sign. The crate will be accelerating upwards, so we have the tension force acting on it, the weight acting downward, and again taking the sum of the forces, we have this equation. And so we can set the two accelerations equal to each other because we know the rope's not going to stretch. And we can actually solve this if we assume that the pulley has no mass, because in that case it says that the tension T1 is equal to tension T2. Now let's look at that a little bit further. We've just said we can do this if the pulley mass is ignored. Let's see why. Because if we include the mass of the pulley, when we do a free body diagram of the pulley, um, well, actually not a free body diagram because I haven't shown the pin forces here, but you can see if I'm going to take the sum of the moments about the center point O, that the only way I can have a non-zero sum of the moments is if T1 is equal to T2. And if there is a mass moment inertia non-zero, ice of O, and there's going to be an acceleration, angular acceleration alpha, then the only way that can happen is if they're unbalanced tensions. And so there aren't, we said before, there's not going to be slipping here. So with this equation and the sum of the forces, we now have enough information to solve the problem. With the finding the tension forces, this is kind of a byproduct of that. Now, if we don't need the tension forces, there's actually a better way to do this problem. Let's look at the whole system. If I draw a free body diagram, you can see I've got the pin forces that hold up the pulley, and the weight of the man and the weight of the crate are the only other things, other forces, external forces acting on this system. The tension becomes an internal force. On a kinetic diagram, remember to show I times alpha of any body that is rotating, which in this case is the pulley, and the mass times acceleration of any masses that are accelerating. So I can take the sum of the moments about point O. Now I can't set them equal to just IO times alpha because that's not the center of mass of the entire system. It's also not the center of rotation of the entire system. In other words, we treat it more like a general point. So when I take the sum of the moments about point O, I include from the free body diagram the distance, which we're just assuming is the radius, even though I've shown the man slightly offset from that. The radius times the weight of the man minus the radius times the weight of the crate from the free body diagram. On the other side of the equal sign, we have the things from the kinetic diagram. The mass moment inertia of the wheel times its angular acceleration, plus the radius times the effective force, the mass times the acceleration of the man, and then the other effective force, the mass of the crate times its acceleration, again offset by the distance r. So because of the fact that we know there's a relationship between alpha, the acceleration of the man, and the acceleration of the crate, we can solve for alpha directly from this one equation. Now when we go to the next class, we're going to use energy methods for the next couple of classes to be able to solve some of these problems.